So, hello बच्चों, सत श्री अकाल and namaste from my side. JEE mains results are out. So heartily congratulations to you all from my side. So this was a retro style congratulations. Second, the daily soap Saas Bahu serials. Congratulations. धूम ता ना 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 क्योंकि आज रिजल्ट्स है सो आज रिजल्ट्स नहीं है हार्टली congratulations right in the Nirupa Roy style नहीं heartily congratulations. Right, lots of students have scored very well, okay, especially from the VW, and number of the selections are there. Yes, okay, this is a series that is extending up to the infinite. That's why I'm saying the end number of the selections are there. Okay, so first of all, sorry for I'm being late, right? Extremely sorry, right, because this lecture was about to come on this day only, and you've seen the congratulations video also. So guys. And yeah, heartily apologize from my side for the teaser as of some technical difficulties, right? Teaser went on suddenly, okay, it was stopped suddenly, so heartily apologize from my side. Okay, lots of discussions with the teams are going on, okay, and we are deciding to keep it as a separate series, okay, but positive things are going to come up soon, so don't get worried. Okay, so guys, we have reached up to the work, energy and power and to the victory batch. So again and again, congratulations to all of those students in all of those styles, retro styles, right? Again, one style is remaining. Congratulations. Congratulations, senorita. Right. Nana Patek. अच्छा है. Result अच्छा है. अम्बरीश पुरी चले वरी दादा मुनी अच्छा है. So feeling good, feeling joy. That's why lots of moods are there. Sorry for wasting right 4 to 5 minutes. How much? Yes. Oh bro, 3 minutes 38 seconds we have missed. Okay, so guys, we are going to start up with a one-shot lecture, work, energy and power. In this lecture, we are going to move forward. Okay, so celebrations were going on, plus please don't get over exaggerated. Okay, don't be in overconfidence. Okay, still second attempt is there. Okay, so those who haven't achieved, please don't be sad, right? We are having again a chance, and final things will be out soon, right? So stay tuned to PW and enhance your preparation. Stay tuned, right? Victory batch, after victory batch, lots of things are going to come even onto the app. The advanced preparations are going on, right? Okay, so funds aside, and if any sentiments of any persons are hurted, I heartily apologize from my side, right? अच्छा है बहुत अच्छा है सर बहुत नौटंकी है. Okay, so finally let's move on to the concept of the work, energy and power and the respective sums. So what we are going to cover up today, we are going to cover the work done. Okay, work done by all forces we are going to cover. After this, right, the most important theorem, right, energy, it's okay, but the most important theorem, that is the work energy theorem. The work energy theorem helps us in the concept of 6th chapter, into the rotation, into the gravitation, into the fluids, right, into the electrostatics, into the capacitors, into the collective electricity, somewhat into the magnetism. Energy is everywhere. Every term, everything into the physics can be explained into the 3 terms, right? Tesla, this is what the Tesla said. Okay, so the most important work energy theorem from the exam point of view we are going to see, and direct question solving approach, and apart from this we are going to see the power and the collisions, right? So shall we begin? Yes or no? We are going to start with the work done. Result came. What work we did, right? Entire 2 years of the preparation went on. Okay, entire 2 years of the preparation was behind it. Entire 2 year of the preparation, right? Wah. Okay, see, work done, it means if I'm defining the work done into the day-to-day life, into the very simplified form, right? If I'm moving on for the supermarket to buy some groceries, right, for my home, okay, on my mom's word or mom's command, work is done. Else, right, if I'm not doing that task, then entire day I'm sitting idly with my mobile. Right, this happens now if you're not doing your task, whatever that is commanded by your mom, right? So if you do, it's okay. You are मेरा बच्चा, मेरा शोन्ना, right? Okay, so if you misbehave or do something extraordinary, then पूरा दिन खेलता रहता है, like that. So to do something is work in day-to-day life, right? To do something, I'm not moving on to the that much technical approach right now. To do something, sir, what kind of something? We are doing a lots of things, right? Yes, this is a work. I'm not saying it is a productive or it is a wastage of time, but you are doing something, it means you are doing work. Work is also having two senses, na? Right? There are always the two faces of coin. There is always, right? There isn't a single face of a coin. There are always two faces. Okay, so we are not saying you're doing a positive work and getting the, what we can say, the appropriate output. We are just saying to do something, you are doing, to do something, it means you're doing a work. Whether it is sitting idly and scrolling Instagram reels, kacha badam, like that way. Okay, whatever it should be. Okay, sorry for this. Sorry from my side. It was an urgent call. So guys, to do something, it is nothing else but in work. According to the NCERT, right? According to NCERT, work done is the dot product of force and displacement, right? Dot product of force and displacement, it is work done. Dot product, cross product, the basics of the vector we all are aware of. Okay, dot product, cross product, the basics of the vectors. How to identify the direction of the cross product, right? Which law is associated with the dot product and which law is valid for the cross product, and everything we have seen. Okay, so now this was a basic definition of the work. Now in terms of the work, if I want to classify, and I'm going to tell you all, the work done can be, this is F dot D, it can be F D cos of theta. F D cos of theta, where F is a force, D is a displacement, cos theta is angle between force and displacement. F is force, D is displacement, the cos theta is angle between the force and the displacement. When work done is positive, negative, 0. Three simple classifications are there. Work done is positive, work done is negative, work done is 0. When work done is positive, first case, F is negative, D is negative, cos value is positive. Work done is positive. Second, F value is positive, D value is positive, cos theta value positive, work done is positive. Sometimes in some of the resources, the books, it is also mentioned when the force is in the direction of the displacement, work done is positive, and force is in the opposite direction of the displacement, the work done is negative. Right? This is what somewhat the detailed explanation of when we are having the positive work done, we are having the negative work done, or we are having the zero work done. Positive work done, negative work done, or the zero work done. Negative work done, right? Force in the opposite direction of the displacement. Let's say force is positive, right? Or let's discuss one of the examples of it. Okay, rather than to have that much complex approach, right? Okay, let's discuss one of the examples of it. Suppose here, right, this is a force, right? This is a magnitude of the displacement, right? Angle between them is 180 degree. So work done, that is equal to F of D cos of theta. The force in terms of magnitude, it is positive. D in terms of magnitude, it is positive. Cos theta, right, it is 180 degree, right? So here when theta is obtuse, this is one of the examples, right? I must say the work done is negative. Zero work done, right? Zero work done. Whenever the force is acting perpendicular to the displacement, whenever the force is acting perpendicular to the displacement, this is a force acting and this is a displacement, right? Here in this case, work is F dot D cos of 90 degree, work done is 0. So these are one sort of example. Suppose if the body is at rest, V is equal to 0, displacement is 0, work done is 0. Right? Force is perpendicular to the displacement. Work is 0. See, these are the one of the examples of what we are discussing about the work. Apart from this, work can be classified into the conservatives and the non-conservative forces. Work can be classified into the conservative and the non-conservative forces. It can also be classified into the work done by the constant forces and work done by the variable forces. Three different sections are there. Work done can be positive, work done can be negative, work done can be 0. Work is defined for the conservative and non-conservative forces. Right? Okay. Work is defined for the conservative and non-conservative forces. Okay, it is a very simple terminology, and in among all the work is done by the constant force and the variable force. Three different medias are there in which we are going to discuss in that the detailed manner about the work. Conservative forces and non-conservative forces. Before moving on to this, we need to discuss what are the conservative forces, and what are the non-conservative forces in detail. Conservative forces. Non-conservative force. Right. What are the conservative forces? The most important characteristics of the conservative forces we are gonna prove. First, they are path independent forces. We are going to prove that they are path independent forces. Don't get so much worried. Path independent forces. Non-conservative forces are path dependent forces. The best example of the conservative forces are weight, kx, mg, kx, and electrostatic force. They are actually nothing else but the field forces. Mg, kx, fe. kind of field forces. One of the examples to understand it, right? Friction is example, the best example of it. Right? Conservative forces are path independent forces, non-conservative forces are path dependent forces, right? For this kind of the forces, common thing, partial differentiation concept is used. You might have seen into the concept of the basic mathematics, right? The basic mathematics tells some things, right? Something about basic mathematics tells us something about the differentiation. Okay, basic mathematics tells us something about the differentiation. Okay, but for the conservative forces, whenever you are dealing with the conservative forces, right, always the partial differentiation is needed, right? Basically, whenever you are dealing with the conservative forces, the partial differentiation is needed. What is the difference between the right, partial differentiation and the differentiation? Some of the students might be aware of, but we are going to clear this thing, right, whenever we will actually deal with the concept of the conservative forces, right, and we are going to prove, right, we are going to see the conditions, how to identify. Apart from this, right, there exists a number of the forces in universe apart from this. So how to identify if any random equation is going to come upon, how to identify whether that force is conservative force or not, right? Whether that force is conservative force or not. Okay. So these are some basic terminologies. Okay. Apart from this, see now, this is one of the example of the conservative and the non-conservative forces. You can see, let us take an example. If particle is at the A position and it wants to reach the B position. Particle is at A position and it is want to reach to the B position. Okay. First particle took path number 1, then second, then third, fourth, 5th, 6 is a straight line, 7 and 8. 8 different paths particle took while for moving from A to B. 8 different paths. Let's compare this to the day-to-day life example, right? Suppose I am moving on from Bombay to Delhi through 8 different parts. Let's say to Bombay to Surat from through 8 different parts, right? Is it possible that moving through all of those paths, daily I am starting at 10, right? Selecting a path and I am reaching at 2. Is it possible for 8 of the days I am going to start at 10? Right, and going to reach at 2. It is possible that I'm going to start at 10, but it is impossible, right, that moving on through all paths each day, I am definitely going to reach at 2. It's not possible. So generally by seeing this, we can say, generally, right, by seeing this, we can say that, what we can say, sorry, lecture is about to published on YouTube late, but right now I was receiving calls from team because JEE results right, preparation is going on, that's why. Okay. So guys, I want to tell you all that, okay, we were on the see, conservative and the non-conservative forces. I gave you all an example. Generally there is a difference in work done in all paths. Generally there is a difference into the work done into the all paths. But while moving on from Bombay to Delhi or while moving on from Bombay to Surat, right? Let's say a short example of a Bombay to Surat, right? Conservative forces are not acting. They are external forces, or somewhere the non-conservative forces are involved. So as of that reason, all of those paths are having the different work done. But if I'm talking about if mg does the work, if kx does the work, right? If electrostatic force does the work, if all of those three right, if all of those three does the work, then it is stored into the form of potential energy. Why? Because they are conservative forces, right? They are path independent forces, right? Okay, this is applicable. This is not for conservative forces, this is only for the non-conservative forces, right? Okay, so mg does the work. It is stored into the form of the gravitational potential energy. Kx does the work. It is stored into the form of elastic potential energy. Fe does the work. It is stored into the form of electrostatic potential energy. Gravitational potential energy, elastic potential energy, electrostatic potential energy, right? They are path independent forces. If I'm talking about, if while moving on from A to B, non-conservative forces are there, work done is different for all path. But if conservative forces are doing work while moving on from A to B, all are same. While work done for the why? Because the work done into the conservative force only depends on initial and final points. Okay. Work done depends on initial and final points. Right? This actually depends on path and its nature. So this is one of the best examples, right, to understand the concept of the conservative and the non-conservative forces, right? Okay. Let's deal with one of the work done by the the conservative forces. Okay. Spring force is a conservative force, right? Spring force is the conservative force. Why? See, right now this is a spring. Initially, the spring is in natural length. Spring is in its natural length. Initially, the spring is in its natural length, right? Suppose if I am applying the force to compress or elongate the string, it is going to expand. What happens here? See, spring is the kind of the helical structure. Spring is the kind of the helical structure. In helical structure, suppose at the one end if force is applied, first what will happen? This much amount of the spring is going to get elongate, delta x. After that, again the next part is going to elongate. After that, the next part is going to elongate. After that, the next part is going to elongate. After that, next part is going to elongate. Like that way, slowly, entire spring is going to elongate. Slowly, entire spring is going to get elongate. So for that reason here, whatever the spring is an elastic object, so restoring force is developed inside the spring. Elastic objects are having the tendency, whenever the external force are applied to the elastic object, there is change in configuration in it. But they have the tendency that on application of the external force, immediately they tend up to come upon the original position. Right? Immediately they tend, right, to come upon the original position. Restoring force, helical structure. So here it is an elastic object. So whenever external force is applied, first delta x will elongate, then another delta x, then another delta x, then another delta x. So for that reason here, whatever the restoring force is developed inside the spring, it is directly proportional to delta x. Sometimes delta x value is quite small. F is directly proportional to delta x. Sometimes delta x value is quite small. Delta x value is quite small. So in this case, what is going to happen? Here force is directly proportional to x. Now this is right depending on x. You can check it out. The force is depending on x. It means the force is varying with respect to x. So this is nothing else but the variable force. This is nothing else but the variable force. Right. So how we are going to define the work done for the variable force? Okay. How we are going to define the work done for the variable force? It is very simple. dW is equal to, right, F dot d of x. dW, that is equal to, right, kx, right, d of x. Right. This is how work is done, how work is calculated, right, for the variable force. Okay. Many things we are going to cover up into the numericals. Don't get worried. Okay. Lots of things we are going to cover up into the numericals. So it's kx dot dx. So work done, that is integration of kx dot dx, right? It is initial point to final point. So this work done is equal to half k, right, x final square minus, right, x initial square. Right. Suppose initially it starts from 0. So we can say it is half kx square. This is work done. Okay. And here kx is involved. This is work done. And then in this kx, the conservative force is involved, right? So it will be stored in form of potential energy. It will be stored into the form of the potential energy. And that potential energy, it is known as elastic potential energy. That is half kx square. Generally, it is defined as half kx square. For the constant forces, we are having the direct formulas that we can calculate it, but this is for the non-conservative forces. Sorry, for the variable forces. Now see, slowly about the work done, we are going to see the sums, right? And just check it out. I am extremely sorry from my side here. Through multiple examples, we are going to see work done for the constant force, work done for the variable force, right? The partial differentiation concept, how work done is calculated for the graph. Lots of things we are going to see. So for that reason, see, work done is a very simple explanation. Many of the students are even aware of. You have even seen this thing into the 9th standard also. There is just a difference, but right now, right, our foundation team is providing you the lots of knowledge. Right, I guarantee that approximately 30 to 40% of the students, right, they might be even aware of what actual the conservative and non-conservative forces is all about. So it's good, right, to what we can say, to solve the sums and clear out those concepts. Force F is 20 plus 10 yx on the particle into the y direction. See, by seeing the expression of the force, we are able to identify. By seeing the expression of the force, we can easily identify that this force is a variable force. Why? The force value F is equivalent to 20 plus 10 of y. F is equal to 20 plus 10 of y. Right? Okay, then it means it is nothing else but the variable force. The value depends on y. Work done by this force to move on to the particle from y is equal to 0 to y is equal to 1. What will be the work done? Y is equal to, while moving the particle from y is equal to 0 to y is equal to 1. Right? Okay, it's a very simple thing. It is a variable force. Directly we have to apply, write the formula of the work done by the variable force. dW, that is equal to F of dy. Generally this formula is represented into the vector form, but right now the force is only acting into the y direction. In another sense, we can say this is the y component of the force. Description regarding the force it is given, and that is acting only into the y direction. So directly we are applying this formula. Otherwise, the general formula is dW is equal to F dot D of R. In another sense, it is F dot del X of I plus del Y, or you can say like this way. This is a general formula. Okay, so what will be the work done? W is equal to integration of 20 plus 10 of y, right, into dy, moving on from 0 to 1, right, moving on from 0 to 1. So this W, that is equal to 20 of y plus 5y square, moving on from 0 to 1. Okay, on integrating this we got, so this work done, that is equal to 20, right, plus 5 minus 0. Okay, the work done, that is equal to 25 joules. Okay, the D is the perfect answer for this specific question. A very simple question asked, right? So for all kind of the variable forces, now students might be having the question into them, and how to identify whether which one is there is a condition to identify in between the conservative and non-conservative. There is the logical sense to identify in between the variable and constant. In between the variable and constant, you can immediately identify force. Either it depends on X, Y, Z, or three of them. And it can be easily, what we can say, corrected out by saying the expression. Similarly, or we can say, yes, analogy to it. If you want to classify in between the conservative and non-conservative forces, we are having the conditions that we are going to see into the later part of this session. Okay, let's move on to the next question onto it. See now, graph. Force F on a particle moving into the straight line varies with the distance as shown into the figure. The work done on the particle while displacing from 0 to 12. Work done is area under the force versus displacement graph. Right? Work done is always the area under the force versus displacement graph. Right? The thing you want to calculate, it's okay. Can I say this? See now, this is a dotted line, right? Displacement 0 to 3, displacement is there, but no force is going on. Right? 0 to 3, displacement is there, but no force is going on. So now what students are going to do, right? They are going to say this is A1, this is A2, this is A3, right? So this work done is area under the graph, that is A1 plus A2 plus A3. Work done is nothing else but the area under the graph, A1 plus A2 plus A of 3. Actually, right, it's all about, actually this thing is getting misprinted. Here 6 is there and here entire line is there. Okay. So for A1, we can say it as 3 into 2, length into height. Again for this 3 into 2, right, plus A3, that is half into 6 into 2. Okay, so this is gonna be approximately 3 into 2, 6 plus 6 plus 6. That net work done, it is going to be the 18 joule. A is the perfect answer for this specific question. This is how work is done, right? Work done is calculated under the F versus X graph. Now what happens if the Fx graph is getting changed? I'm going to give you all another example of it. right? Let's see whether it has been mentioned. Okay, no, it is not mentioned, but let's see. Okay, let's have the another graph. I'm going to show you all one another example. Suppose graphs are of the different natures. Suppose here this is f versus x graph, and it is mentioned we need to calculate, right, the work done from x is equal to 0, right, to x is equal to 1, and the graph is like this way, parabolic kind of a graph, or it is like another graph or the hyperbolic one, whatever it should be, whatever it can be. If this kind of, see, apart from any symmetric graph, anything comes up into the examination, immediately it should get, you all should have an click right into your mind that this is a case of the variable force. So in that case, right, work is going to, we are going to calculate the work with the formula dW is equal to F dot dx. Now here, this is a parabola with respect to the x-axis. It means that F will be directly proportional to x square. This equation we are going to use and to find up the answer. Right? So here dW is equal to F dot dx, replacing the value of F, I'm going to get it as K as constant, it is x square dx. Right? So this work done, that is equal to integration of kx square d of x, that is equal to k, right? It is x square of dx, limiting from 0 to 1. So this work done, that is equal to k, right, by 3, where k is a constant value. This is how work done is calculated into the area under the, see, this area under is like this way, right? Area under the fx graph is a work done. But if it is a symmetric, then easily we can calculate the area. But if we are having the curve kind of thing, right, then area is always y dot dx. Right, for a curve kind of thing, for same thing, see, y dot dx, we got it on, right? Work done is equal to integration of f dot dx, right? We can compare this. Okay, so this is a way, right, through which the work is calculated with respect to the graph. Let's move on to the next part. A body of mass 3 kg is under the constant force which causes a displacement, and that displacement is given by this equation. What is work done by the force in 2 seconds? Generally, what approach students are going to follow and what approach, right, we are going to follow, I'm going to clarify the actual difference between them. Okay. See, generally students will follow S is equal to half of 1 by 3 of t square. Velocity is equal to 2t by 3. Acceleration is t. In between 0 to 2, it means acceleration is 2 meter per second square. Right, and work done is equal to MAD. Yes sir, we got the answer and it is in option. Take it. This is not a correct approach. This is not a generalized approach that is applicable for all questions. Okay, this is not a generalized approach that is applicable for all number of the questions. Not a generalized approach. So what we are going to do, we are going to follow the work energy theorem in this case. Work done by all forces, that is equal to change in kinetic energy. See, whether on the system one force is acting or more than one forces are there, we are not aware of. It is only mentioned constant force. In some of the cases there may arise more than one, right? In all of those number of the questions, it is not for sure that same procedure we need to follow. Differentiate and following the velocity and moving on to the acceleration, right? It only happens when acceleration is constant. But whatever the approach we are going through right now, it is applicable for all kind of the question. We are not aware of what kind of the forces are there. Even we are not sure about the acceleration. So in that case, anyhow, if we are able to calculate the change in kinetic energy, work done will be calculated. Always follow this approach. Always calculate the change into the kinetic energy, right? Immediately you will reach up to the work done. Okay. So displacement equation is given as 1 by 3, right, t square. Let's differentiate this equation with respect to time. We are going to get velocity as ds by d of t, that is equal to 2t by 3. At t is equal to 0, velocity is 0. At t is equal to 2 seconds, velocity is 4 by 3. In between two time intervals, right, we need to calculate the work done. For the same two time intervals, we are having the values of the velocity. Now things are going to be quite easy. Mass is 3 kg. So half into 3, what is final? 4 by 3, that is 16 by 9. What is initial? 0. So that is equal to 3 by 2 into 16 by 9. 3 3s are 2 8s are. Work done is 8 by 3 joule. D is the perfect answer for this specific question. Let's move on to the next question onto it. See, another graph came. Force F is acting. What is the work done while moving from x is equal to 0 to x is equal to 6? Area under the graph. Right. This is A1. This is A2. Right. So what is this? Is 3 into 3 plus half into 3 into 3. So this is 9 into 3 by 2. That is 27 by 2 joule. B is the perfect answer for this specific question. See now, force is a variable force. F is equal to 7 minus 2 of x plus 3x square. At x on the small body, we need to calculate the work done from 0 to 5. So W is equal to integration of f dot dx moving on from 0, right, to 5. Integration of 7 minus 2x plus 3x square, right, d of x moving on from 0 to 5. The work done into the joule is W is equal to 7 of x minus 2x square by 2 plus 3x cube by 3, right? So this is moving on from 0 to 5. 3 3 2 2 is gonna get cancelled, right? So work done, that is equal to 7 into 5 minus 25, right? Plus 125. So this work done is 35 plus 100, 135 joule. A is the perfect answer for this specific question. How many type of forces are going to do the work? In this chapter, right, we are going to see actually into the summarized form. The simple definition of the work is F dot D cos of theta. The force can be of any type. Force can be conservative, non-conservative, constant force, variable force. Some of the examples of it like mg, kx, normal, tension, pseudo, friction, work done can be of the any type. Simple, you have to remember this formula, and this is used into the multiple ways, right? The formula is used into the multiple ways and things are getting resolved. The formula is used into the multiple ways and things are getting resolved. Yes or no? Okay, formula is used into the multiple ways and things are right resolved. Work done into the type of forces. W is equal to F dot D cos of theta. Right, F dot D cos of theta. We are going to see, but before that, see. This is the simple thing we have discussed already. Now we are moving forward to the core part of this chapter, that is work energy theorem. The next 1 hour of this lecture, right, we will deal with the concepts of the work energy theorem. Okay, next 1 hour of the lecture we are going to deal with the concepts of the work energy theorem, right? And we are going to see how work energy theorem. See, important thing is not what actual the work energy theorem is all about. Important thing is how to apply the work energy theorem. How applications are asked into the examination. See, I have made up one approach, right? To solve maximum number of the sums of the work energy theorem, right? I have made one approach. That approach we are going to discuss for next 1 hour of this class, and obviously I'm going to show you all using that approach and how the maximum number of the sums are going to get resolved. Right. So what actual, see, this is a very important part in the physics syllabus. In this chapter, we are going to use the work energy theorem. Into the upcoming chapter, we are going to use the work energy theorem, right? Some of the questions even of the NLM can be solved using the work energy theorem. Even in gravitation, we are going to use that. After gravitation in thermodynamics, yes, into the different way we are going to use that work energy theorem. The rate of the work done. Okay, the rate of the heat flow. After that, this thing we are going to use in SHM, fluids, into the 11 electrostatics, capacitors, current, electricity, everywhere this kind of theorems are used. Only the forces are getting, the nature of the forces are changing, and a bit of a concept. Now, what does this work energy theorem says? The work energy theorem states that, let us take an example. This is block of mass m here, force F1 is acting here, force F2 is acting here, force F3 is acting, right here, force F4 is acting. The work energy theorem want to states that any particle who is performing a motion, any kind of the motion, or in any physical activity that is going on, the n number of the forces are present, right? N number, or in another sense, numerous forces are present. Numerous forces are present, right? Okay, in any activity that is going on. Any activity that is going on in surrounding, numerous number of the forces are present. So what does this work energy theorem say? If particle is in motion, velocity is getting changed. Particle is in motion, the velocity is getting changed. Similarly, what does this theorem states? It states that work done by all forces will change into the kinetic energy of the object. Work done by all forces will change into the kinetic energy of the object. Work done by all forces are going to change the kinetic energy of the object. Now here, it depends on what activity is going on, right? On basis of that, we are going to identify which force is involved into the work done with what amount. On analyzing the application and depending on the activity that is going on, we are going to identify which force is involved into the work done and of for what amount. How much contribution? See, for any activity, n number of forces are there. So it means n number of contributions are there. Contribution might be small, great, whatever it should be. It can be zero also. But we can only identify, right, on depending on the. Sometimes it happens the force is acting, but particle is not moving. Suppose here F2 and F3 are not there. Only F1 and F4 is there. If both are acting opposite in direction with the equal in magnitude, then the forces are acting, but the particle will not move. So it means that net work done is zero. Why? Net work done is zero because change in kinetic energy is zero. First of all, we are going to discuss that part into the detail, and I'm going to show you all the steps of it. So first of all, let's discuss that part into the detail. Work done by all forces that will change in kinetic energy of the object. Depending on the application, right, work done by all forces are defined. It can be work done by conservative forces, work done by non-conservative forces, right, work done by external forces, right, okay, that is equal to change in kinetic energy. Maximum number of forces that are into the syllabus are involved in this. Again we are having a problem, right, again we are having the problem. The work done, if conservative forces like mg, right, kx, electrostatic force, if this does the work, then this work done, it is stored into the form of the potential energy. So whenever the conservative forces are doing the work, it is stored into the form of the negative of the potential energy plus work done by non-conservative forces, work done by external forces, that is equal to delta K. So here work done by non-conservative forces, work done by external forces, that is equal to delta K plus delta U. By rearranging the terms, we got this as the equation. So work done by non-conservative forces, work done by external forces, that is equivalent to delta K plus delta U. Okay. Work done by non-conservative forces, work done by external forces, that is equivalent to delta K plus delta U. Now, this is the general equation, the generalized approach that we have to use for all of the applications of the work energy theorem. This is only the equation I have discussed. How to apply it, we are going to discuss within few minutes. Right? How we are going to apply this, we are going to discuss into the few minutes. Now, suppose example of the non-conservative force is friction. Example of the external force, it is F. It can be of the any value. It can be constant, it can be variable. So this is suppose friction is not present. External forces are also not present. The frictional forces also, non-conservative forces also not present. Then delta K plus delta U is 0. If this happens, it means that mechanical energy is conserved. whatever the variations are going on, it is going on in between the kinetic energy and the potential energy. So this is the spatial approach in which the mechanical energy is conserved. The spatial approach in which the mechanical energy is conserved. Only these two equations we are going to use. We are going to see the steps involved into it. But apart from this, how and when these two equations are applied, this each and every student should have sense of. Each and every student should have sense of how these equations are going to applied. Now, I am going to write down some steps, and those steps are applicable for the maximum number of the questions, right, that are involved into the conservative, or the maximum number of the questions, those who are the applications of this kind of forces. First, always check in application the presence of, always check in application the presence of the non-conservative and external forces. Always check in application the presence of, right, the non-conservative forces. If non-conservative forces are absent, right, and external forces are also absent, it means that work done by non-conservative and work done by external forces is zero. Follow the equation of mechanical energy conservation. Delta K plus delta U is equal to 0. K initial, U initial, K final, U final, right? This is total energy at initial point, total energy at final point. If non-conservative and external forces are absent, immediately you have to follow the second equation. Mechanical energy is conserved, right? Wherever no dissipative forces are there and no external forces are there, right? Immediately you have to follow this equation and you have to reach up to the results. If F external is not equivalent to 0, F the non-conservative forces is not equivalent to 0, then we have to follow the approach that is non-conservative plus external, that is equal to delta K plus delta U. Delta K plus delta U. Right or wrong? Yes or no, guys? So there are some three, evaluate and get the results. Right? Yes or no? So check it out. The same approach we are going to, using this approach we are going to solve all of those sums, right? I think approximately how much? Okay, more than hour of the classes has been gone. right? Using this approach in next 30 to 40 minutes approximately of this class, we are going to use, right? Using this approach, we are going to see lots of sums. Lots means lots of sums, right? Now, let's start with a very simple approach. Hope so before moving on to this, right, you all should be aware of how potential energy is there. Now it is applied. See, a particle of mass 10 gram moves along the circle of radius 6.4 centimeter. Okay. Particle of mass 10 gram moves along the circle of radius 6.4 centimeter with a constant tangential acceleration. What is the magnitude of the acceleration if kinetic energy becomes the double or becomes equal to this at the second of the revolution? Let's say particle starts from position A, it completes the 2 rounds and come back to the same position. Right? At that time the kinetic energy, see here, only tangential acceleration is there. We can't say tangential acceleration when there is always a presence of the centripetal one. Okay, there is the presence of the centripetal one. Okay, actually this is a part of the circular motion, but I'm going to only give you all the approach of it. Okay, because I think randomly it has been kept, it's okay. So what happens here? Work done. See, there is a presence of external force here, tangential acceleration. The force associated with this is an external force. Right? If the particle is moving on to the circular path with a constant magnitude of the velocity or a constant velocity, magnitude of the velocity, right, then the tangential acceleration is not involved. If tangential acceleration is involved, it means the external force is there. There might be possible that there is no presence of the non-conservative forces, but external forces are present. So in that case, work done by the external forces, that is equal to change in kinetic energy. Right? Mass into net acceleration, we can keep it as only acceleration. Okay, now after completing the 2 revolutions, right, the displacement is, right, 4 pi r, that is equal to half m v final square minus v initial square, but here the kinetic energy is given as 8 into 10 to the power minus 4. Right, mass is 10 gram, so 10 into 10 to the power minus 3 into acceleration into 4 pi, right, that is r is 6.4, so 6.4 into 10 to the power minus 2, 8 into 10 to the power minus 4. Right, so I think this one is going to cancel this, and this 2 and this 2 is going to cancel this up. Right, so a into 4 pi into 6.4, that is equal to 8. So a is equal to 8 whole divided by 4 pi into 6.4. Right, a is equal to 8 whole divided by 4 pi, right, into 6.4. So what will be the perfect answer for this, guys? Right, what will be the perfect answer, right, for this? Okay. So this is nearly, I think, 8 pi square under root of 10. So first this is gonna be 2, right, this is gonna approximately, it is going to be 0.09, or we can say it is nearby equivalent to 0.1 meter per second square. C is the perfect answer for this specific question. C is the perfect answer for this specific question. First we saw work, now we are seeing energy, how energy is involved. Bullet of mass 10 gram leaves the rifle at the initial velocity of 100 meter per second and strike with the velocity of 500. It leaves at 100, strikes at 500, velocity is decreased. It means there is a presence of dissipative forces. Step 1, check. How we are going to check? Velocity decreases immediately. First equation. Work done by non-conservative forces, work done by external forces, that is equal to delta K plus delta U. The work done in overcoming the resistance of air will be what? Okay. See now, right? The bullet is fired from the ground. Obviously, it is going to right cover some large amount of the distance and then going to strike back the ground. So in that case, we can say delta U is quite negligible. Okay, and friction is also not there. So it means only we can say the external force, that is equal to half m v final square minus v initial square. Right? Half m v final square minus v initial square. So this is what going to work. That is work done. That is equal to half 10 gram. That is 10 into 10 to the power minus 3. Right? That is final minus initial. Right? Okay. So it's 500 into 500 minus 1000 into 1000. Right? 500 into 500 minus 1000 into 1000. Right? So suppose we are saying that is equal to 10 to the power minus 2. Right? 2. We are saying 500 into 500, we have kept it as constant. Right? We have kept this as constant. Okay, so this is gonna be 1 minus 4, that is minus 3. Okay, so this work done, that will be equivalent to 500 into 500, right? Negative of 3 whole divided by 200. So this is gonna get cancelled, right? 250s are work done, that is equal to negative of 750 into 3, right? Okay, negative of 750 into, sorry, 25 5s are 125, I'm sorry. Okay, negative 25 5s are 1250. Work done is negative of 3750 joule. This is the work done that is changing the velocity of the bullet. But in question it is asked how much work in done is joule is needed to overcome the air resistance. This is right the work done that is changing the velocity of the particle, changing the kinetic energy of the particle. It means this is a work done by air resistance. To overcome this, we need to apply the positive 3750 joule. Right? And B is the perfect answer for this specific question. B is the perfect answer for the specific question. Yes or no? B is the perfect answer for the specific question. Let's move on to the next sum onto it. A mass M is attached to the thin wire and whirled. Okay, this is a motion into the vertical circle. We're going to see afterwards. See now. A body initially at rest and sliding down the frictionless track H. Okay. Now you just complete the vertical circle of the diameter AB is equal to D. Then height is equivalent to what? Step 1. Check the presence of dissipative and external forces. Surface is smooth. No friction, no conservative. External forces are there, it is just released, no external forces. So step 1 we check it out, no external forces are there, no dissipative forces are there. Immediately we are going to use that equation. Mechanical energy is conserved, kinetic energies, right, and the potential energies at the initial and final point are going to be equal. Now this is an important stuff, how we are going to apply this. For potential energy, always the reference point is needed. Potential energy is always calculated with respect to the reference point. Potential energy is always calculated, right, with respect to the reference point. Generally, we are taking ground at the reference point. See, this is a gravitational potential energy, na? Okay. How this equation is applied? Select the 2 points about which you need to apply this work energy theorem. This is the initial point. This is a final point. In between initial and final, with respect to this two, we should have the reference point. So generally, we are taking the ground as the reference point. The reason behind taking the reference point, because potential energy, right, is always calculated with respect to the reference point, whether it is elastic, whether it is electrostatic, whether it is gravitational potential energy. So how we are going to solve this stuff? At initial point it is released. See how we are going to apply this equation. K initial, U initial, K final and U final. At initial point it is just released. Kinetic energy is 0. At initial point it is at the height h. It means the gravitational potential energy is mgh. Above reference point potential energy is positive. Below reference point potential energy is negative. At a reference point potential energy is 0. Slowly when it comes down at point B, it means it came nearer to the reference point, so the potential energy is 0. Entire potential energy got transformed into the kinetic energy. So at the bottom we are having the velocity of under root of 2gh. Half of the sum is solved. Half of the sum is solved. Now, when it reaches the bottom, it is having that much amount of the velocity that it completes the vertical circle. It is having that amount of the velocity that it completes the vertical circle. It means at the bottom, this much amount of the what velocity we got na, it is equivalent to, it is sufficient to complete the vertical circle. It means it is nearly equivalent to the under root of 5gr. Then and then it can come down and complete the vertical circle. So here h, you are going to get it as 5r by 2, right? And if you want to write down in terms of the diameter, then h is equal to 5, right, d by 4. The D is the perfect answer for this specific question. This is how, right, the work energy theorem is applied using, right? In applying the work energy theorem, obviously the steps I told you all, it is an important. The calculation of the potential energy is also important. Let's move on to the next sum onto it. Spring is already compressed. Ball is attached to it. Spring is already compressed and ball is attached to it. It is at the elevated point of height h. Surfaces are smooth. At what point? It will strike on ground. At what point it is going to strike on the ground? At what point it is going to strike on the ground? It is a very simple thing that we are going to discuss. Okay. Now what happens here? Step 1. External force is absent. Right. Conservative forces, the non-conservative forces are also absent. It means that mechanical energy is conserved. Initially, whatever the work has been done in compressing the spring, it is stored into the spring in the form of potential energy. It means spring is maximum compressed and it is having enormous amount of the potential energy. Step 1, external forces are 0, everything is 0. It means we are going to follow the conservation of mechanical energy. Right, this will be the initial position, right, and somewhere when spring will be right into the natural position. Okay, so this will be our final position, right, in which spring will be in natural length. So what happens here? K initial, U initial, K final, U final. K initial, U initial, K final, U final. Initially we are having the right elastic potential energy, no kinetic energy, ball is at rest. Final we are having the kinetic energy half mv square. Now final at a point where spring is in natural length, no restoring force, no elastic potential energy into the spring, no potential energy. And here if we are talking about the reference point, then this is a reference point, okay, about which with the potential energy, the gravitational potential energy is calculated, but here everything is going on at the one surface level. It means no potential energy is involved. So kx square is equal to mv square, right? So it is v is equal to under root of k by m into x. When it is released, the spring is in natural length. Particle got the velocity of under root of km by m into x. Now slowly it is moving forward with the constant velocity. Finally on reaching up the edge, it is projected with the horizontal velocity, and you will follow the horizontal projectile motion. The point at which it is going to hit the ground, we are going to calculate the range. So the range that is equal to u under root of 2h by g. So that is equal to under root of 2hk by m of g into x, right? This is the distance at which it is going to strike up the ground. So this is how the work energy theorem is used. Okay, this is how the work energy theorem is used. Question says, an object is released from height h. Okay. It is the object of mass m is above the platform, right, of height h, and it is released. So it strikes the platform and compresses the spring. This question is quite simple. We need to calculate the maximum compression in spring. Question is quite simple. Check it out. Step number 1. Friction? No. External force? No. How to select the reference point? Selecting the reference point for the potential energy, it's your choice. Generally, what students used to do, they select the ground as the reference point for the potential energy. But choose wisely. Always choose wisely so that can decrease your calculation step. Suppose in this case, if you are selecting the ground as the reference point, are you aware of the length of the spring? No. Then, right, it's wrong to select the ground as a reference point. So what will be the smartness? To select the platform as the reference point. Why? This is gonna be initial position, right? Now spring is going to maximum compress and m is going to come upon here. This is going to be the final position. Initial position, height h is there. Final position, maximum compression is x. So this is one variable, this is one variable. Using these two variables, easily we can write out the equation. Right? Easily we can write out the equation. So it is important to choose this reference point wisely. Else you are going to get stuck. Else you are going to get stuck. So in this case, what is going to happen? Directly we are going to apply initial kinetic, initial potential, final kinetic and final potential. Initial kinetic, initial potential, final kinetic and final potential. At initial position with respect to the reference point, see it is released. Velocity is 0. It means we are not having any kind of the kinetic energy, 0. Are we having potential energy here? Two type of potential energies are involved. First, the gravitational potential energy, and second, that is an elastic potential energy. Gravitational potential energy is there, yes, with respect to the reference point, object is at the height h. Elastic potential energy is there, nakko. What about the final position? Particle, the object is stable, no kinetic energy. In this, our potential energy involves, yes, two type of potential energy. One, spring is maximum compressed. So it means elastic potential energy is involved. Half kx square, where x is a maximum compression into the spring. Second, object went below the reference level. It means negative gravitational potential energy is involved. mgh plus x is equal to half kx square. Kx square minus 2mg, right, h minus 2mg x is equal to 0. X square minus, right, 2mg by k into x minus 2mg h by k is equal to 0. Quadratic equation is formed. Using this quadratic equation, we can calculate the value of x. And x is nothing else but a max compression into the spring. So using that approach, see how the right equations are applied. Using this approach, you can say the approach we discussed for the work energy theorem. Using that, you can understand how things are gonna get applied. Now we are going to see some of the chain problems involved into it. Some of the chain problems involved into it. Suppose the question is there, this is a ground on which fixed groove is there. We are having 2 points. This is a point A. Chain is lying on the groove. Initially, the chain is lying at the rest on this groove. The radius of the groove is r. Surfaces are smooth. A gentle push is applied. Tuck. Gentle push is applied. If gentle push is applied from the point A, entire chain is going to come like this way. So we need to calculate the velocity of chain at A on applying the gentle push. Surfaces are smooth, no external forces. Gentle push, it means no external forces there. Mechanical energy is conserved. K initial, U initial, K final, U final. This is the initial position. This is the final position. This will be our reference point. The length of the chain, that is equal to pi of r. Length of the chain, that is equivalent to pi of r. Now what happens here? Initially the chain is at rest, so it means the kinetic energy of the chain is 0. How you are going to calculate the potential energy? See, into the previous cases what we saw, this was an object, right? A dimensionless object. It is having no dimensions. It is, you can consider this as a particle. Particle is at the height h, so you are using mgh, right? In this previous case, particle was at height h, directly we are using mgh, we can use it mgh, right? In this case also, right, particle was at height h, in this, right, we were using mgh. But here, if this particle is into the continuous body, if this particle is nothing else but the continuous body, then distance of the reference point to the center of mass is taken as the h. See, potential energy, it is nothing else but the mgh, you all are aware of. But how you are going to calculate this h? H for the continuous body. So that h is the distance between the center of mass and the reference point. So in this case, this h is gonna be mg. This is a ring-like structure. So the center of mass for the semicircular ring is 2r by pi. Chain is ring. Final kinetic energy when the string is completely vertical, half mv square. Now what will be the final? See, only one gravitational potential energy is involved. This is a reference point. Negative potential energy is going to come at L by 2. Center of mass for the whole chain, for the continuous body, is at L by 2. So this is going to be mg, value of h is L by 2. L is pi r. Mg, 2 mg r by pi, that is equal to half mv square minus mg into pi r by 2. M is gonna get cancelled. 2gr by pi, right, plus pi gr by 2 is equal to v square by 2. So what is the velocity at A? V is equal to under root of 4gr by pi plus pi of r. This is going to be the value of the velocity at point A. This is going to be the value of the velocity at the point A. This is how the work energy theorem is applied for the chain problems. Now I am going to give you all one homework for it. Suppose the chain is lying like this way. If gentle push is applied, at A, find the velocity of chain at point A like this way, right? This is the homework based question and you need to answer beneath the video, right? This is the homework based question and you need to answer beneath this video. Okay, so this was all about the, okay, apart from this, there is one, the special case of the chain problem, okay, in which this kind of the questions are asked and it is having the direct formulas. Right, it is having the direct formula. Okay, what kind of the formula it is? The question states that if chain is lying like this way on L by nth part hanging, okay, chain lies on horizontal table with L by nth part hanging, calculate work done, right, in pulling entire chain on table. So here in this kind of the cases, right, on basis of this is L minus L by N. A direct formula is that mgl by 2 of n square. Suppose here L by 3 part is hanging. If it is L by 3 hanging, n is equivalent to 3. The work done, that is equal to mgl by 18. Like this way, on depending the value of the n, the work done is calculated. Right. So this is a kind of the, right, the special case, right, on one of the application, right, of the work energy theorem. The special case or the one of this is only the approach you are going to apply the work energy theorem into the gravitation and all of those chapters. Okay, the same approach we are going to follow on applying the work energy theorem into the multiple, right, things. Now, so this was all about the work energy theorem. Now we are moving forward to the actual concept states that an object of mass m, it is tied with a string like this way, right? Suppose let's take a very simple example that I am having in front right now. Okay, let's have this, right, to understand the concept very well. Okay, it's done, right? Okay, see, object is like this way, right? Suppose it is released from the bottommost position with the horizontal velocity, like this way, it is released, right? Okay, suppose at the bottommost part the u velocity is given and it is following the vertical circle like this way. This activity, right, this whatever the phenomena it is going on, it is known as motion into the vertical circle, right? Motion into the vertical circle. Now, what is an actual concept? The actual concept, it is one of the applications of work energy. Two most important questions: variation of tension, right? Variation of velocity, right, with respect to the angle theta, with respect to vertical or the bottommost far from where the particle is projected, right? The minimum velocity needed to complete the vertical circle, right, and some of the conditions related to it. This all of these things we are going to discuss, right, for the motion into the vertical circle concept, right? This all of these things, right, we are going to discuss for the motion into the vertical circle concept. Now, first of all, let's move on, right, to the equation of velocity. Suppose from the bottommost point, particle is given the velocity as u meter per second, right? Obviously, it is following the vertical circle like this way, right? Is following the vertical circle like this way, right? Now, how the velocity is changing, right, with respect to the angle theta. Suppose at the bottommost velocity we are having u, particle is at this position, the position of the particle is changing on the right vertical circle. So how the equation of the velocity we are going to define it? Suppose this is the point that is making angle theta with respect to the vertical, right? That is making angle theta with respect to the vertical. Okay, so in this case, So what will be the variation into the velocity? Sorry, right? Suddenly I received a call. Extremely sorry. Right, lots of things are going on. That's why, right? The new surprises are going to come. Okay, so don't get worried. They are all like good things for you. Okay, very good things. Okay, so you suppose at the bottom it is released at the u meter per second. So at this point, right, obviously it is going to have velocity v. So with respect to theta, how we are going to identify the relations between u and v? Same work energy theorem we are going to use. Step 1. This will be our reference point. If you want to take this as a reference point, it's okay. If you want to take this as a reference point, it's okay. But by taking this as a reference point, one term, one expression of the potential energy on the either side will get increased. Right? At the end, it is going to cancel out. It is going to nullify, but we have to write it down. So it's good to take the reference point, this as the reference point. So this is an initial position, right? And this is the final position. So can I say there is no resistive forces, right? No dissipative forces are present. So immediately the energy is conserved. The mechanical energy is conserved. So at initial, potential energy is 0. Kinetic energy we are having half mu square. At final, right, with respect to the reference point, suppose this is a reference point, particle is like this way, right, making some angle theta. So can I say this is L cos theta, right? This is L cos theta, right? This suppose this is L. This is making 90 degree. So this is theta. So this will be L cos theta, right? But with respect to the reference point, we need this height. So can I say that is L minus L cos theta, that is L1 minus cos theta, right? So the final, it is half mv square plus mgl1 minus cos of theta, right? So rearranging this term, we are getting v square, that is equal to u square minus 2gl1 minus cos of theta, right? So the variations of the velocity, right, okay, or the velocity at any point, it is given like this way. This is the equation. Can I consider this is equation number 1? Yes. At the same point, we are going to discuss what is the minimum velocity needed so that it can complete the vertical circle. Right? Minimum value. Okay, first of all, let's move on to the concept of tension first. Right? Now, how the variations of the tensions we are going to determine in this. Same. At the bottommost point, u meter per second, it is given. It is completing the vertical circle, right? Now, between point A, right, and point B, how tension is getting varied? Between point A and point B, how the tension is getting varied, right? How the variations of the tensions are taking place, right? How? It's a very simple thing. Okay, now let's move on. At the bottommost point, can I say tension is acting into the upward direction, mg is in this direction, and mv square by r centripetal is in upward direction. While, sorry, mu square by r. While at this point, tension is in this direction, right? Centripetal mv square by is in this direction and mg cos theta is in this direction, right? So suppose if I want to use the Newton's law at the point B, can I write the net force is centripetal force mv square by r, right? That is equivalent to T minus mg of cos of theta. So tension at that point, see tension at any point that is changing with respect to theta, that can be given as, this is the reference point. Okay, theta is calculated with respect. So tension is equal to mv square by r minus mg of cos of theta, right? Can I consider this is equation number 2? Yes, this is equation number 1. Can I replace equation number 1 in 2? replacing equation, write 1 in 2. What we get? Replacing equation 1 in 2. What we get? T, that is equal to m by r, right? U square minus 2gl. L you can consider it as a r. L and r both are the same thing, right? L, R both are the same thing, right? It's okay. So m by r, that is u square minus 2g r1 minus cos theta. Minus mg cos of theta, right? So this is m u square by r minus 2 mg r by r 1 minus cos of theta, right? And that is again, this is minus, right? So it is minus mg cos of theta, right? Solving this, we are getting T is equal to mu square by r. This r is going to cancel, right? Okay. And okay, 1 minus cos theta, minus is going to be plus. So this is minus 2 mg, right, plus 2 mg cos of theta, right? Okay. Sorry, this is plus. I'm sorry. This is plus. I'm extremely sorry. This is plus. And that is plus mg cos of theta. This is plus. Because this is moving on to this side, we are getting it plus. Sorry. So T is equal to mu square by r minus 2 mg plus 3 mg cos of theta. So the final equation of tension, we are getting mu square by r minus mg 2 minus 3 cos of theta. This is how tension is varying with respect to the bottommost point and angle, right? This is how velocity is changing with respect to the bottommost point and the angle. Suppose this is the equation of the tension we need to use. Suppose if we need to calculate the variation, see on the vertical circle, right? If you need to calculate the variations of the tensions between A and B, simple, right? Tension at A, right? Suppose this is our reference point and with respect to this we are calculating the theta. So at this theta is equal to 0 degree. So it's mu square by r minus mg, right? 2 minus 3 cos of theta. Cos is 0. So tension of A is mu square by r minus mg, right? 2 minus 3 cos of 0. Cos of 0 is 1. So tension at A, that is mu square by r minus mg, right? And 2 minus 3 is minus 1, right? Cos of 0 is 1 na, so 2 minus 3 is minus 1. Minus will be plus. So tension at A, that is equal to mu square by r, right? Plus of mg. Can I consider this is equation number 1? Yes. Now, how to calculate the tension at B? Because we need to calculate the difference between them, na? Right? So TA, TB, right? That will be again mu square by r minus mg 2 minus 3 cos of theta. Suppose if I'm talking at B with respect to A, angle is 180 degree. Unnecessary, again and again we don't have to apply the conservation and we have to apply the Newton's second law. No, we are having the direct equation, we can use that. So TB, that is equal to mu square by r minus mg cos of 180, that is equal to 5. This is minus 1, this will be 5 mg. So TB, that is equal to mu square by r minus 5 mg. The tension between B and A, right? Or sorry, in between A and B, I'm sorry. Okay, tension between A and B, how to calculate? Simple, we are having the two equations in front, right? So TA, that is equal to mu, sorry, TA minus TB, okay? I'm sorry, TA minus TB, right? We are going to get the difference, okay? TA minus TB, that is equal to mu square by r plus mg minus mu square by r plus 5 mg,
right? This is going to cancel. TA minus TB, we are going to have 6 mg. This is a tension difference between the 2 points on the vertical circle with respect to the reference point, that is the bottommost. Like this way, you can calculate you can take any reference point. It's not a big deal. You can calculate the tension difference between any 2 points. Suppose if you want to calculate the tension difference between A and C, at A you have to replace the angle as 0, at C you have to replace angle as pi by 2. Right? So this is how the variation. Similarly, if you want to calculate the velocity difference, we can calculate. Right? By what formula we can calculate? By using this. At the bottommost point you can replace the theta. At the topmost point or else point you can replace the theta. Now, in the motion in a vertical circle, this was the equation of the tension. Right? Now, what is the minimum velocity required? Right? Okay. Suppose, what is the minimum velocity required at the bottom, right, so that it can complete the vertical circle? To complete the vertical circle, obviously we need that much amount of the velocity so that it can reach up to top. At the top, tension is in this direction, mv square by r is in this direction, right, mg is in this direction. So at the top, right, tension will be completely zero. So can I replace the equation of the tension, that is mu square by r, right? Okay. Mu square by r minus mg 2 minus 3 cos of theta. We need to apply the enormous amount of the, right, the needed amount of the u so that it can just touch the, it can just reach the topmost part of the circle. It can just reach to the topmost part of the circle. So at the topmost part of the circle, theta is 180 degree, and at the topmost point, tension will be 0. That is mu square by r, that is minus 5 mg, right? So u, right, minimum needed 5 gr, right, for particle to reach top or complete vertical circle. If you are applying minimum under root of 5 gr at the bottommost point, it is going to reach at the top also, and it is going to complete the vertical circle. In some cases it differs, but generally we are taking this term. So what is the minimum? Minimum velocity needed, that will be equivalent to under root of 5 gr. Minimum velocity needed, that is equivalent to under root of 5 gr. Okay. Now, question solving approach. First, equation of the velocity v is equal to under root of u square minus 2g L1 minus cos of theta. Second, variation of the tension, that is equal to mu square by r minus mg 2 minus 3 cos of theta. Right. Minimum velocity needed, that is at the bottommost point under root of 5 gr. Right. Okay. Yeah, and apart from this, lots of things are there, right? How much minimum velocity is needed? Suppose this is point A. How much minimum velocity is needed to reach the point A? Just reach under root of 2g. How much minimum velocity is needed so that it can cross point A? How much minimum velocity is needed right at the bottom, so it can be in between A and B? The table is there. U under root of 2gr, under root of 3gr, under root of 4gr, and lots of resources, many things are there. But according to me, you have to just remember two things. At the bottommost point, if you are applying under root of 2gr, it is going to reach at the point A. Just reach at the point. If you need just two things, you should remember. If you want that this particle should reach at the topmost point of the circle, minimum you need to apply it under root of 5gr. And if you want that it should reach point A, minimum at the bottom you should apply it under root of 2gr. Apart from this, suppose here the value needed is 2gr under root. Here value needed is under root of 5gr. So in between this two, right, variations will happen. in thousands of the resources, thousands of variations are given, right? And students always, oh, this table is quite important, and they used to mug up and mug up. No, no, no. Just simple two things. Under root of 2gr, you know, to just reach here, and under root of 5gr to just reach at the topmost point. Right? Now, this is the concept of the motion into the vertical circle. Now we are directly, right? We have left two sums of the this work energy theorem that was completely based on the motion in the vertical circle is application. This one, yes. A mass m is attached to the thin wire and whirled into the vertical circle. The wire is most likely to break when, right? At what point into the vertical circle? See, this question is asked in 2019 NEET examination. At what point into the vertical circle we will have the maximum, sorry, the wire is, right, will get breaked. The maximum amount of the tension that is generated into the, produced into the wire will have the maximum possibility to get break. So suppose at the bottommost point, tension is like this way, right? And here it is mg and here it is mv square by r. So at point A, if I am applying the equation, we are having mv square by r, that is equal to t minus m of g. So t is equal to mg plus mv square by r, right? This is what happening at point A. If I'm talking about the topmost point, right? mg into downward direction, centripetal into downward direction, tension into the downward direction. So at B, mv square by r, that is t plus mg, right? So t is equal to mv square by r minus mg. You can see the difference between A and B. At A, tension is more as compared to B. And obviously at the other points, right? Okay, at the other points, obviously tension is going to differ. Here we are having t is equal to mv square by r, right? So obviously we are having only 2 points to analyze, the bottommost point and the topmost point. And in between the bottommost and topmost point, even you can see, right, at position A, we are having the maximum amount of the tension. So in that case, if we are having maximum amount of the tensions, and there is only the possibility, at that point only the string can break. It is just a lowermost point. When the mass is at the lowermost point, the tension is more, there is a highest possibility for a wire to get break. Right? There is a highest possibility of a wire to get break. This is a release from the top. Now see, this question is asked in NEET 2018. This is a release from the, first of all, let's determine the reference point. This is a reference point where potential energy is 0. This is a release from the top. Now it is reaching at the bottom. From what height it should release? See, a body is initially at rest, sliding down the frictionless track. Friction is not present. It means from work energy theorem, mechanical energy is conserved. Directly we can use this equation Ki ui Kf uf. Between the initial and final points, total energy is constant. From what height it should release so that it should complete at the bottom. From what height it should release so that it can reach at the bottom mass part and complete the vertical circle. This is an initial point, right? Let us consider this as a final point. In between initial and final, let's apply the energy conservation. K initial, U initial, right? K final, U final. At initial, it is just released. So kinetic energy is 0. At initial, we are having potential energy as mgh, right? By reaching there, we are having kinetic energy is half mv square, and we are reaching right to the reference point, so the potential energy is 0. So here v square, that is equal to, right, 2gh. After reaching the bottom, right, we are having the velocity as under root of 2gh. But to complete the circle, how much amount of the velocity we needed at the bottom? At the bottom, we are having under root of 2gh. But to complete the vertical circle of radius r, right, we need under root of 5gr minimum velocity. Right? So to complete the vertical circle under root of 5gr, r means d by 2, we need r. They have asked in diameter, that's why. This much amount of the velocity is needed, right? This much amount of the velocity is needed. But at the bottommost point, we are having under root of 2gh. There is issue. Needed velocity is this, but we are having this. So it means if you want to complete that vertical circle, this two should be equal. So evaluating this, you are getting h as 5d by 4. D is the perfect answer. If it is released from 5d by 4, it is going to come down and complete the vertical circle. NEET 2018. So these were the two questions, right, that we saw. Now we are going to move on to, okay, chain. Again, NEET 2016, phase 1. What is the minimum velocity with the body mass m must enter the vertical loop? Simple. Bottommost point minimum velocity needed, right? So at the topmost point tension should be 0. mu square by r minus mg 2 minus 3 cos of theta. We need to find the value of u, right? So at the topmost point tension is 0. So 0 is equal to mu square by r minus ng at topmost point. Cos is 180, right? So you are getting u minimum as pi gr. Simple. NEET phase 1 2016. This is a homework from my side. This is also the nice sum. This is based on the equation of the velocity that we discussed right now. Right, so I will be waiting for our answers here beneath the video, right? I will be waiting for this answers right beneath the video. Okay, now as shown into the figure, the particle mass is performing the vertical circular motion. Average velocity of the particle at which point string will break. We are having only, we discussed at the bottommost point tension, we are having T is equal to mv square by r plus mg, right? While at the topmost point, right, we are having that is mv square by r minus mg. So there is only one possibility that at the bottommost point, right, okay, this tension may get maximum and the string may get break. Okay. Power. Boom, boom, power. Boom, boom, power. Power, what actual the power is and how we are going to define that stuff, right? Do you know the woman empowerment, right? The thing that is going on, okay, on the pic right now, woman empowerment, what actual the woman empowerment is all about? Right? Okay, power. Marvel. Miss Marvel. She's powerful than Thanos. Power is what? Simply we are defining rate at which work is done. Two people are there. I am telling both of them to reach USA, right? Okay, or we can say I am telling both of them to reach Canada. Apna Canada. It's not Canada, right? Apna Canada. Feeling. Apna Canada. I am telling both of them to reach Canada.
The one is selecting a direct flight from Delhi to Canada. The second one is first of all moving on to the, let's say one is selecting the flight from Delhi to Dubai or Mumbai to Dubai, and from that he is directly moving on to the Canada. The second one is moving on from, first of all he will move on to the Kazakhstan. From Kazakhstan he will move on to the Spain, Turkey, and after that he will go on to the Amsterdam, and after Amsterdam he is moving to Canada. So who is the person who is going to reach early? Rather than focusing on reaching early, who is having the highest rate of doing work? Right? That defines the power. Entire power concept. Power is having the limited number of the sums, and we are going to see, we are not going to waste time on it. Power is having the limited number of the sums, and all of those sums of the power are based on this formulas. Right? We are going to see that right into the short period of time. Don't get worried. We are going to see all of those stuff. Okay. So the rate of the work done is power. F dot V dot product of force and velocity in some of the books, that is mv by dv by dt. Body of mass m 1 kg begins to move under the time dependent force. What power will be developed by the force at the time t? What power will be developed? Right? See, simple. The force is the variable force. What actually it is? 2t of I plus 3t square of j. Force is 2t of I plus 3t square of j. What we need to calculate? We need to calculate the work done. dW, that is equal to F dot D of R. One of the applications of the work done that was remaining. Force is depending on X also and Y also, because here both of I and J unit vectors are involved. So how we are going to calculate the dW? Right? How we are going to calculate the dW? Okay. So this is gonna be force. It is 2t of I plus 3t square of j dr, that is dx of I plus dy of j. Right? Okay. So here dw you are going to get it as, okay, 2t, okay, dot. But rather than moving on to this approach, okay, here we are also, rather than moving on to this approach, the force value it is given, na, right? The force value it is given. What we need to calculate? We need to calculate the power, na. Okay, so, okay, this is power, that is equal to F dot V. Okay, it is F dot V. Okay, so rather than following this approach, we are going to obtain, let's follow the acceleration approach. Right? Let's follow the acceleration approach. Okay, see, acceleration, that is equal to force by mass. Mass value is 1. Then acceleration vector you are going to get it as 2t of I plus 3t square of j. From this velocity vector you are going to get it as a t square of I plus t cube of j. So this is the velocity vector we got. Now if you want to calculate the power, see, I told you all, it depends on only this formulas. F dot V. What is the force? 2t of I plus 3t square of j dot product of t square of I plus t cube of j. I dot I 1, j dot j 1. Power is equal to 2 t cube plus 3t to the power 5. Right? Okay. What? 2t cube plus 3t of 5. B is the perfect answer for this specific question. Okay.
Let's move on to the next part. Particle of mass m is driven by the machine that delivers the constant power in k watts. Power is constant, that is equivalent to k watts. Right? If the particle starts from rest, the force acting on the particle at time t will be what? What is the force acting on the particle? See, formula of the force, that is equivalent to m into a. So that is m into dv by dt. Right? Anyhow, right, if I'm able to calculate this value, okay, I'm able to calculate the force. Anyhow, I have to reach. So directly we can say this is mv dv by dt, that is equal to k, the third formula of power. V dv is equal to k dt by m, integrating on both sides, starting from rest to v, starting from 0 to t. V square by 2 is equal to kt by m. V square is equal to 2kt by m. Right? V is equal to, right, 2kt by m whole to the power half. Right? Now V is equal to 2kt by m whole to the power half. We got the V, but let's differentiate with respect to time, that is half 2kt by m into minus half into 2k by m. 2 is gonna get cancelled. dv by dt value is going to come upon as k by m into 2kt by m into minus half. Now we need to calculate the force. Force is equal to mv dv by dt. So this is m. What is the value of v? 2kt by m whole to the power half. Right? And what will be the value of sorry, it is not mv dv by dt, it is only, right, m dv by dt. So it is m into k by m, 2kt by m whole to the power minus half. M is gonna get cancelled. It is k, right, 2kt by m whole to the power minus half. But here it is written into some else form. So we have to represent, okay. So it's k, 2k, I'm sorry. It's m by 2kt whole to the power half. It's mk square whole divided by 2kt whole to the power half. 1k is gonna get cancelled, right? So here f is equal to m of k, right, okay, into 2kt whole to the power, I'm sorry, 2t, mk by 2t, mk to the power half, 2t to the power minus half, right? Mk to the power half under root of mk, right, and t to the power minus half. This is the perfect answer. Sorry, half will come, I'm sorry. Okay, half will come. Okay, this is the perfect answer for this specific question. This is how the questions of the powers are resolved basis on it. Okay, one question of the power I'm going to give you all into the homework. This is a homework. This has been asked in mains 2012. I want answer of the homework video beneath the video. Write into the comments. Okay, so this was all about the power. Now let's move on to the next concept, right? The next concept of the motion into the vertical circle. Okay. A very simple example, right? Okay, see, till now we have seen what is work, what is energy, some of the concepts related to the work energy theorem and lots of examples related to it, right? Some of the concepts of the power and blah, 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 right? Motion in vertical circle. Now this is a very small concept that is remaining, right? Okay, collision, its classification, its nature, type of collision, and 2 to 3 formulas are there, not more than that, right? 2 to 3 formulas are there, not more than that. See, collisions means what? right? Accident of car and truck. Collision. Slap. Collision. Right? Have you ever played that carom? Right? It's one of the example of the collisions. Right? So whenever the two right bodies interact with each other, right? Interact with each other, I must say they are colliding in any way, right? The best example, GIF is in front. There is no, like, lots of technical definitions and thousands of resources are there, right? But we are not going on to that much detail. The collisions, it means, right, two particle interaction. Okay, two particle or two object or two rigid bodies interaction. That's it. Okay, see now. There is a difference. There is a difference. Accident of a car and truck, it is different, right? While playing a carom, right? While playing a carom, if the striker strikes, that collision, it is a different. While playing a pool, when two billiard balls collide, that collision is different. So there exist many types of collision. There exist many types of collisions. How to identify the nature of the collision? For that, we are having the most important term, that is coefficient of restitution. The coefficient of restitution defines, right, whether the collision is elastic, inelastic, plastic, right? Okay. So before moving on to the this nature of the collision, let's move on to the first of all the classification of it. First, elastic collision, right? Inelastic collision, right? Perfectly inelastic collision. Elastic collision, right? Inelastic collision, perfectly inelastic collision. Elastic collision, inelastic collision, perfectly inelastic collision. Then how am I able to differentiate that? Collisions of two billiard balls, right? There is no energy loss. And if I'm comparing that example to a car accident with truck, lots of energy losses there. So the main fundamental, right, behind this classification of the collision is energy loss. Energy loss will define, right, the nature of the collision, and energy lost will actually classify, it will help us in, right, the classification of the collision. First, no energy loss. See, to understand this example, so to understand this stuff, let's take an example first, then we are going to write down the noteworthy points. Suppose, let us take a very simple example, right? This is particle 1, mass m1, moving with velocity u1. This is particle 2, mass m2, and moving with velocity u. This is the situation before collision. After collision, this is mass m1 moving with velocity v1. This is mass m2 moving with velocity v2. Before collision, after collision. Before collision, after collision. Before collision, velocities were u1 and u2. After collision, right, velocities are v1 and v2. My question, is there any kind of the energy loss or not? Suppose if I'm taking the example of the billiard balls, they are moving forward. If the two collides and after collision the velocity is getting changed, in that energy loss is minimum. No energy loss. Theoretical, we are having no energy loss, right? So that case is of the elastic collisions. So in elastic collisions, in elastic collisions, we are having no energy loss. The kinetic energy of the system before and after is same. Kinetic energy is conserved. Second point. I'm talking about the system. If I'm talking about the whole system, right? If I am talking about the whole system, net external force is 0, right? Net external force is 0, right? Net external force is 0 for a system. It means momentum is also conserved. Right? Elastic collisions, no energy loss theoretically. Kinetic energy is conserved, right? Net force on the system is 0. It means momentum is also conserved. In inelastic collision, energy loss is there, right? In inelastic collision, right? Okay, energy loss is there, right? Kinetic energy is not conserved. Momentum of the system is conserved. Kinetic energy is not conserved because energy loss is there, but momentum of the system is conserved. Perfectly inelastic collision. Maximum energy loss. The first particle sticks to the second after collision. Car accident. First, it gets sticked. Maximum energy loss. Particles stick together. This is a word, right, that is used for inelastic collisions, right? Sometimes in question it is not mentioned which type of the collision it is. So for that we are having the specific word. Particles get stick together. Maximum energy loss, particle gets stick together. Kinetic energy is not conserved. Momentum is conserved. But momentum of the system is conserved. Right? See, first of all, we moved on to what actually the collision is, right? After we saw this classification. But this classification is based on the energy loss and some of the noteworthy points. Now, I want to actually define the nature of the collision. For that, we are going to use the same example. Before collision, particle is of mass m1 moving with velocity u1. Particle is of mass m2 that is moving with velocity u2. After collision, particle of mass m1 that is moving with velocity v1. Particle of mass m2 that is moving with velocity v2. So before and after collision. Before and after collision. Apart from energy, right? Apart from energy loss, right? The coefficient of the restitution, this will help us to determine the nature of the collision. So the actual formula of the coefficient of the restitution is, right? E is velocity of the separation by velocity of approach. This is for one, or you can say one particle system that is colliding with some stationary object or of the heavier mass. The another formula for the two particle system, we can define it as E is equal to V2 minus V1 whole divided by U1 minus U2, right? The terminology stands same that has been abbreviated in these examples. It means u1, that is particle 1 initial velocity, u2 particle 2 initial velocity, v1 particle 1 after velocity after the collision, and v2 is right velocity of the particle 2 after the collision. So this is what the coefficient of restitution, like coefficient of friction, how surface, how rough the surface is. That's coefficient of friction. Coefficient of friction, static friction, how the surface is having the ability to hold an object, right, even while the external force is applied. That coefficient of static friction, that determines the nature of the roughness of the surface. Similarly, coefficient of restitution, that determines the nature of the collision. If it is elastic collision, the coefficient of the restitution value is 1. It means that velocity of separation is equivalent to velocity of approach. If it is inelastic collision, the coefficient value is in between 0 and 1. Velocity of separation is not equivalent to velocity of approach. Right? Here, velocity of separation is not equivalent to velocity of approach. Right? Perfectly inelastic collision, coefficient of restitution is 0 and velocity of separation is also 0 because the particle gets stick together after the collision. So this is what the entire detail, right, of the collision is all about. We have defined the collision in terms of energy conservation. We have defined the collisions in terms of the coefficient of restitution, right? We determine the values of the restitution also. But there are some two important formulas related to it, right? Two important formulas related to this collision, and things are getting resolved first. Again, we are going to take the same example, right? We are going to take the same example. This is a situation before the collision and this is a situation after the collision. In all of the types of the collision, the system, right, on the system, the net external force is 0, so momentum is conserved, right? For all type of collisions, momentum is conserved, but only for elastic collisions, the kinetic energy of the initial and final kinetic energy of the systems is conserved. And for rest, there is an energy loss. See, before particle, this was mass m1, this was moving with the velocity u1, this is m2 that was moving with the velocity u2. After collision, this is m1, right, it is moving with velocity v1, this is m2, right, moving with velocity v2. We need a common formula of a particle. Say this kind of the questions are there into the examination, right? And they are asked as a PYQ. I'm going to show you all just after this derivation. Right now, we are in need of a formula that can be used, right? That the general formula for all types of the collision, and that can be used to solve this sum easily. Net external force on the system is 0, momentum is conserved, right? Can I write it down? Momentum is conserved, so m1 u1, m2 u2, that is equal to m1 v1 plus m2 v2, right? In lots of books, lots of derivations are given, but into the very few resources, right, this formula is mentioned and it is a very important one. What will be the value of the coefficient of restitution? v2 minus v1, and that is equal to u1 minus u2, right? This is what the right restitution is. Okay, now e u1 minus e u2 plus v1, that is equal to v2, right? The main motive for this derivation is, right, to find the velocities of the object right after the collision. General formula. So can I consider this as equation number 2, replacing equation number 2 in equation number 1, right? Replacing equation number 2 in equation number 1. What we get, right? That is m1 u1 plus m2 u2, right? Can I replace the value of the right, m1 v1 plus m2 e u1 e u2 plus v1, right? Now we need to solve this. m1 u1 m2 right, u2 is equal to m1 v1 plus m2 e u1, right, minus m2 e u2 plus m2 v1. Right, from this we need to identify the value of the right v1. So here it is m1 u1, right, and minus, okay, m1 u1, okay, plus m1 u1 m2 u2, so anything v2 e u1 minus e u2, okay, so here minus this term m2 e u1 plus m2 u2, right, and this is plus m2 e u2, that is equal to v1 m1 plus m2. From this, velocity of the first particle after the collision, that is m1 minus e m2 whole divided by m1 plus m2 u1 plus, right, m2 1 plus e whole divided by m1 plus m2 into u2. This is the velocity of the first particle after the collision. First particle after the collision. Now this is a generalized formula, right? If elastic collision is going on, replace the value as E is equal to 1. If inelastic collision is going on, replace the value of the E will be in between 0 and 1. If inelastic collision is going on, replace the value of E as 0. Now, again, rewriting this equation, right, we'll get V1, that is equal to V2 minus EU1 plus EU2. Can I replace this equation in equation number 1? So to get the velocity of the second particle after the collision. So it is M1 U1 plus M2 U2, that is equal to M1, right? What it is? V2 minus EU1 plus EU2, right? Plus M2 V2, right? So we are replacing all of those stuff, right? We are replacing all of those stuff to get the equation velocity of the second particle after the collision. And finally, I will rewrite this equation above, right? Finally, right, I will rewrite this equation above, right? I'm going to rewrite this equation, okay? Don't get worried. So now here it is M1 U1, right? Okay, plus M1 E U1, M2 U2 minus M1 E U1, right, is equal to M1 plus M2, right, V2. So we are getting the formula of V2 as, right, M1 1 plus E whole divided by M1 plus M2 U1 plus M2 minus E M1 whole divided by M1 plus M2, right, U2. This is the velocity of the second particle after the collision, general formula, right? I'm writing down above, right? So it will be quite helpful for you all, right? See, before collision, the velocities were U1 and U2. We need to calculate the velocities after the collision. So using the conservation of momentum and the coefficient of restitution approach, we got the velocity of the first particle after the collision as M1 minus E M2 whole divided by M1 plus M2 U of 1 plus, right, M2 1 plus E, right, U2 whole divided by M1 plus M2. This is the velocity of the first particle after the collision. Velocity of the second particle after the collision is here, that is M1, right, 1 plus E whole divided by M1 plus M2 into U1 plus M2 minus E M1, right, whole divided by M1 plus M2, right? Okay, this is U2. This is the velocity of the second particle after the collision. Directly you can use, and we are going to use this stuff, right? So this is all about the momentum of the kinetic energy. Even you want to write down the kinetic energy, right? Then initial, okay, kinetic energy initial, that is equal to half M1 U1 square plus half right, m2 u2 square. Final kinetic energy, that is equal to half m1 v1 square plus half m2 v2 square. This is all about the kinetic energy. But why we are not dealing to that stuff, right? Because this thing is, right, conserved only in elastic collisions, right? So this is what the collisions is all about, right? This is what the collision is all about. Initially, right, we see the collision is the nature of the collision, the restitution, the classifications of this, the momentum and kinetic, and we got the two important formulas. Okay, all see, two interacting particles, masses are given, nature of the collision, right, the restitution is given, u1 and u2 is given, you will get v1 and v2. With this you can get the fractional kinetic energy loss also. See, using this equation, right, we are going to solve that stuff, and this kind of how that formula is going to helpful, right, in solving the question that has been already asked in NEET 2019. We'll see. See, a body of mass 4m is moving with, a body of mass 4m, it is moving with speed u, and it collides with another body of mass 2m, right, which was at rest. So before collision 4m was moving with u, after this 2m was at rest. Right. Now it has been given that collision is completely lasting in nature. Then after collision, the fraction of kinetic energy loss will be what? So for that, we need to calculate the velocities of the particle after the collision. Now we need to calculate the fractional kinetic energy of body A. It means we need to calculate velocity, right, of A after the collision. Now nature of the collision, it is given as completely elastic. It means that simple, right? We want to directly replace the formula. So velocity of the A after the collision is v1. What is the formula of v1? m1 minus e m2. See, m1 minus em2 whole divided by m1 plus m2, and that is u1 plus m2 1 plus e, right, whole divided by m1 plus m2 into u2. Now u1 are initial velocities of the particle. u1 is u, u2 is 0. Now if u2 is 0, then this entire part is going to be 0. Because here u2 is 0 and 0 is multiplied with that stuff. So what will be the value of v1? m1 is 4m. Restitution value is 1 because it is an elastic collision. m2 is 2m whole divided by 4m plus 2m, right, into the velocity u1 is u. So v1 that is equal to 4m minus 2m by 6m into u. So v1 velocity of the collision is u by 3. Velocity before the collision was u. Yes, right. It collides with a particle at rest. The velocity of the collision was u, but after the collision it got u by 3. So what is the fractional kinetic energy loss? The difference, right? That is half m v final square minus v initial square whole divided by half m v initial square. Replacing the values, you will get delta k as 8 by 9. Sorry, delta k by k, the fractional energy loss, right? C is a perfect answer. So see how this formula is quite helpful in solving that stuff. There is one assumption also, not assumptions, it is a perfect result. Suppose if this is a mass m, this is a mass m, initially it was moving with u and this was at rest. What will be the velocity of the first particle after the collision? v1, m1 minus e m2 whole divided by m1 plus m2, right, u1 plus, right, m2 1 plus e, right, whole divided by m1 plus m2, right, into u2. u2 is 0. So v1 it will be right, m minus m whole divided by m plus m into u1. Similarly, if you are applying the formula of v2, then you are going to get as u. What it states, before collision, u1 was u, u2 was 0. after collisions, right, v1 is going to be 0, right, v2 is going to be u. See, velocities got interchanged. Why it happened? It happened only in the case of elastic collision, right, and for the identical masses. In the case of elastic collision and only for the identical masses. Right, in case of elastic collision, only in the case of identical masses. Right, elastic collision, right, whenever the two identical particles are colliding elastically, perfectly elastic, like perfect elastic collisions are going on, then obviously the velocities right along the line of motion will get interchanged. Velocity vectors will get interchanged, right? Not only the values or magnitudes, velocity vectors will get interchanged, right? Okay. So this was the more important stuff, right, that I want to discuss. Now, second question. This question based on the coefficient of restitution that has been asked in NEET 2018. A moving block having mass m collides with another stationary block. See, a moving block mass m, right, that collides with another stationary block of mass 4m at rest. The lighter block comes to rest after the collision when the initial velocity of the lighter block is v. Right, then the value of the coefficient of restitution is what? Moving block of mass m collides with stationary block of 4m. See now, coefficient of restitution is velocity of separation by velocity of approach. It is equal to v2 minus v1 whole divided by u1 minus u2. Right? Now, see what it states. Right, initially m was moving with v, right, 4m was at rest, right, m was moving at the v, right, okay, so can I say u2 as 0 and this was moving as u, or you can say as v, eraser, this is v, right. Now it has been given the lighter block comes to rest after the collision. It means v1 is 0. v1 is a velocity of the first block after the collision. It has been given 0. While u2, the velocity of the second block before the collision is 0. Both things are mentioned. Now we need to calculate, right? We need to calculate what? The coefficient of restitution. Still we are having v2 as unknown. The velocity of the second block after the collision. Directly we are using this formula, right, but still we are not having that. Okay, so we can apply the coefficient of restitution, this momentum conservation. M was moving with v, right, finally plus 4m was at 0. This is initial momentum. Final momentum m got to 0 plus 4m got the velocity of v dash, or you can say v2. Right, so this v2 that will be equivalent to v by 4. Replace this, right, e will be 1 by 4, that is equal to 0.25. Right, the B is a perfect answer for this specific question. See, this is how the momentum is going to help. This is how the coefficient of restitution is going to help. Right, this is how the equations are going to help. Right, okay, lots of things, right, they are going to help. Apart from this collisions, right, there is one more important concept, right, for the 2D. Basically, the classification of the collision is based on 1D and 2D, right? Basically, the classification of the collision is completely based on, right, 1D and 2D. In 2D, there is one simple question solving approach that is going to help us a lot. Only single question solving approach. What it is? Particle is coming with velocity u, making angle alpha. It collides here. I'm not saying which type of the collision it is, and reflect back. we need to generalize this and obtain the formula as we did into the previous part of 1D. Right? Previously, it was completely the head-on collision we discussed. Right? We completely a head-on. This is all about the head-on collisions. Right? Apart from elastic, inelastic. Right? See, elastic, inelastic, perfectly inelastic. Apart from this is having 1D, 2D, 1D, 2D, 1D, 2D. 1D, 2D. This is all about the 1D means head-on collision, right? The line of the motion of the particle is same. That is head-on collision. And this is everything we discussed about this stuff is about the head-on collision. See, collision in 1D. Right? But this you all are aware of, right? The most important stuff regarding the collision is this formulas and whatever the things related to 2D what I'm discussing right now. See, right now I'm not aware of what kind of the situation, what kind of the collision is, what will be the value of E, right? But we are saying this. Suppose it collides and it reflects back to angle theta. We need to calculate the theta, right? And this, see, now. When the two particle collides, right, there are always the two most important factors. The first important factor is common normal. The normal that is common to the two surfaces. Let us take an example. Suppose this particle is moving on this way and this particle is moving on this way. They both collide like this way, right? So this will be the common normal for them. And this will be the common tangent. Normal reactions. As you can imagine, normal reactions like that, common normal. The tangent that is common to them, it is a common tangent. Again, I am showing you one example to understand this stuff, right? Again, I am showing you one example to understand this stuff. Suppose this particle is moving on this way and this particle is moving. They both are going to collide at that, right? So this will be, right, the common normal and this will be the common tangent. It is important, right, okay, to understand the concept of common normal, common tangent. Common normal for two interacting particles, right, the line that is actually normal to both. Common tangent, right, the line that is actually a tangent, the common tangent to the both interacting particles while collision. This is happening common normal and this is common tangent, right? This is while collision, not before and after collision. This is while collision and this is only the concept to solve the sums, right, of 2D collisions into the quite convenient manner, right, of the 2D collisions into the quite convenient manner. While collision, the common normal to the both, the common normal reaction that lies to the line, that line is a common normal and common tangent to the both, right? Now, suppose this is a u sine alpha, this is a u cos alpha. Similarly, when it reflects back, right, this is a x component, this is a y component. Now, first most important point, right, the components of velocity that lies along common tangent never get changed. Tangent is not going to create an impact into the collision. Only the normal, see, if two particles are colliding like this way, right, then the normal between them is only going to create an impact and it is only the responsible for the energy loss. So it means along the common tangent u sine alpha, it is not going to change. Neither the magnitude is going to change, neither the direction is going to change. But second point. Momentum is conserved for components the velocity components that lie along common normal, not common tangent. Momentum is only conserved for a particle that lies along the common tangent, common normal. Coefficient of restitution formula is only applied to velocity components that lie along common normal, not common tangent. It means the coefficient of restitution said velocity of apparition by velocity of approach. So this will be the y component e to the velocity of approach. What is the velocity of approach? The component that lie along the common normal, that is going to create an impact. So velocity of separation is e v cos of alpha. Sorry, e u cos of alpha. So the y component after the separation is u cos of alpha. Right? So what is the velocity of the particle after the collision? That is equal to u sine of alpha of I plus eu cos of alpha of j. You can see the component that lie along the common normal changed ue times. This thing you can see changed e time. Now e completely depends on the value, whether it is 1, whether it is e 0 is less than 1 or everything, right? It completely, it will define the nature of the collision. So this is the best question solving approach of the 2D. For that, right, you need to understand the concepts of the common normal and common tangent. Right? So guys, be aware of it. Right, if someone right is not able to understand this stuff, guys, I'm going to tell you all, just kindly rewind this video and see this again. Okay, because this collisions again we are going to discuss into the center of mass also with the combined rigid bodies. This is a case of the rigid bodies 2D. This is just for an information purpose, right? Apart from this, we have discussed lots of things, right? Head-on collisions and everything. This 2D is just for the discussion purpose. So the reason behind it is because we haven't dealt with the rigid bodies till now. And so if we haven't dealt with the rigid bodies, so we are not going to understand this stuff of 2D. What actually the common normal is, but still, right, you can rewind the video multiple times for this concept, right? You can see this stuff. Okay. So, and from the beginning of the chapter, right? Okay, there are some homework. So students, thanks a lot. So I think this was all about the work, energy and power, right? And this is Indrajit Singh signing off from the desk. Bye bye, Sat Sri Akal and Namaste from my side. So next lecture would be on the center of mass. Lecture would be quite short, but we are going to enjoy a lot. Okay guys, so this is Indrajit Singh signing off from the desk. Bye bye, Sat Sri Akal and Namaste from my side, Bacha ji. Bye everyone, stay at home, stay safe, stay healthy amidst this pandemic. Bye Bacha.